So last time there we started talking about stoichiometry, and we talked about two types of stoichiometry type problems. Really kind of a basic stoichiometry problem. And in a basic stoichiometry problem, as we talked about last time, the way you kind of know it is a basic stoichiometry problem is you're really only given one piece of information in the particular problem. And in that case, you really do follow kind of the four steps pretty much in all stoichiometry problems. You always want to make sure you start with the balanced equation. The equation is important because that gives us our kind of mole to mole relationships here from the actual coefficients. We want to take whatever they gave us basically and convert it to moles. And in most cases, whatever unit it may be in, at some point is going to go to grams, and then it's going to probably go to moles. And once again, it is the molar mass from the periodic table that's going to allow us to do that conversion. The next step is really the stoichiometry step, and that is the mole to mole relationship. As we talked about, really stoichiometry is nothing more than a conversion factor that you pretty much just get from the equation from the coefficients. And again, what it allows us to do is go from one thing in the reaction to something else that we are interested in without obviously a table or something like that. So we use really the balanced equation as a conversion factor. And that's why it's always important to make sure it's always balanced when you do it. Lastly, here in a basic stoichiometry problem, usually we take those moles and we convert it to some other unit. Also very common on the back end of the calculation is to kind of end up in grams in a lot of cases. And again, that would be obviously the molar mass on the back end of the calculation as well, which is very, very common. We talked about the idea of limiting reagents as well, and limiting reagent type problems. We know that they are limiting reagent problems, and really the way that you can determine that is simply you are given enough information about the reactants that you pretty much can get to moles, and whatever units they may be in, you have a way based on information given to you about the reactants that you can basically get into moles of each of the reactants. And that's really the sort of flag that tells you that it is a limiting reagent problem. Now, there's multiple ways you could do these limiting reagent problems, as we talked about. The one way I kind of focused in on is doing an ice table. And an ice table approach, as we saw last time, can be very beneficial because it can allow you to really get to every answer you might want in a particular problem very quickly. Initial change, which we represent with an X, and E is end in this case. So if we were going to do sort of a equilibrium type of, or an ice table type problem here, we would start with the moles of everybody. So really, the first couple of steps here are pretty much the same, no matter what approach you're taking. I would assume zero of this. Remember, it is the change part that's really important. When you do the ice table, you do have to take the coefficients into account, because really that's going to take into account the mole to mole relationship, and it's going to give you the proper stoichiometry. So if you do not do that, then you're kind of wasting your time, because you will not have the right mole to mole relationship. This is going to be minus 2x because the reactants should be decreasing with time. This would be minus 3x, as it's still decreasing with time. Our product should be increasing with time, which would be plus 2x on the back end here. Now, when we go to find which one is our limiting reagent, we basically just need to do a very quick problem on each of these reactants by setting them equal to 0 and solving for x. 2x. And when we do solve for x, we're looking for whichever one is the smallest. And the smallest value of x would be our limiting reagent. And it also would, again, be all of the x values that we see in this particular table, which would then allow us to really solve very quickly how many moles of our product, which we then could get to grams, how many moles maybe of a second product. We can also figure out, which is a very common question that's asked, how much of your excess reagents left over at the end of the reaction. So you can kind of go back without having to do necessarily separate from the beginning sort of calculations to do that. And you can answer those questions really quickly. Again, the alternative approach to this is mostly taught by most people, is just to do two separate basic stoichiometry problems, starting with each reactant separately and figuring out how much product each one would make. It's the same product, obviously, and whichever one makes the smallest amount of product would be both your limiting reagent and your theoretical yield in that case. So that's the other very common sort of approach. The third approach is the one I had on the slides that I put up there, is where you do a stoichiometry problem between the two reactants and try to figure out, do you have enough of one reactant to completely use up the other? And that's the third sort of common approach to these type of problems. So as I mentioned before, I particularly don't necessarily have a preference. If you want to do this way, it's a pretty convenient way to get all the right answers. It also is the calculation, if you plan on taking 200B, very similar calculation to what you'll do in 200B. So if you want a little practice before you get there, that would be very helpful as well. But if you still know a previous way, or like one of the other versions of doing it, you could obviously do it that way, as long as it's a legitimate way of doing it, is perfectly fine. We ended with the idea of percent yield, and percent yield is our actual divided by our theoretical times 100%. Our actual is usually given to us in book problems. So somewhere in the problem, they'll say how much product that you would have produced. And a yield has to be a product. So that's why it's called a yield. Theoretical is based off of how much you start with and the equation and doing stoichiometry. So typically you need to calculate the theoretical yield. And usually in a book problem, the actual is given to you. Again, you just divide the two times by 100, and then you get a percent yield, which, as we talked about last time, we are looking for a high value for a percent yield. We don't really want a low value, and we don't really want a super high value over 100%. Again, that can mean that you have some issues as well. Any questions on any of that stuff there that we talked about? All right, I think we got another one here to practice on, one last little stoichiometry problem maybe for now. All right, let's say if we take 100 grams of ammonia and we react it with 100 grams of carbon dioxide and we produce 120 grams of our product here, what is the percent yield? So let's give it a go. Nitrogen 1401. Okay, let's take a look. So once again, we are given 100 grams of ammonia, which is this guy. We're also given 100 grams of carbon dioxide, which is this guy. So again, with no blinking lights, does it say it's a limiting reagent problem? But I do have the grams of both of my reactants, which means I have no problem getting to moles of both of those. And that means that this is a limiting reagent problem because, again, we're given enough information to get to the moles of each reactant. So that means at some point we do need to do the limiting reagent part, but really no matter which sort of step you take or approach that you take, the first couple of steps are pretty much the same. We're going to balance the equation, which is already done for us. We're then going to take whatever they gave us and convert it into moles. So we'll do the ammonia first here. That's 100 grams of NH3. Go into our periodic table here. We got nitrogen at 1401 plus 3 times our hydrogen. Going to give us 1703 grams per mole for our NH3. So using that as our conversion factor here, 1703 grams per mole for our NH3. We're going to do the same thing for our carbon dioxide in this case. And going to the periodic table for carbon dioxide, we got 1201 for our carbon, plus 2 times 16 for the 2 oxygens that are present. In that case, going to give us 4401, I believe, grams per mole, which will be our conversion factor that we would use for our carbon dioxide. Again, we do want the grams on the bottom so that they cancel. Grams cancel in both cases, and this is going to get me here 100 divided by 1703. We'll call it 5.872 moles of NH3 to start with, and 100 divided by 4401 gives us 2.272 moles of CO2. Any questions up to that point? Now that we have our starting moles here, once again, I'm going to show the ice table approach so you can see it again. We're going to do our ice table. So initially here, we have 5.872 moles. We have 2.272 moles here, 0 and 0 of this guy. Our change will be minus 2x, as it should be decreasing, once again taking the coefficient into account so we have the right mole to mole relationship. This would be minus x, as the coefficient here is 1. On this side, it'll be plus x, coefficient is 1, and plus x as well. The coefficient here is 1. Bringing everybody down here to the end gets us 5.872 minus 2x, gives us 2.272 minus x, x, and x. Any questions on the table here? At this point, we're going to do our really sort of quick calculation, hopefully, to figure out which one is the limiting reagent. We're going to set each of our reactants equal to 0 and basically solve for x. On the guy on the right, that basically just moves the x to the other side and gives us 2.272, and these are moles. Over here, that gives us 2x is equal to 5.872. Divide the 5.872 divided by 2. Going to give us a 2936, it looks like, here, moles. Again, we are looking for the smallest x value, which is this guy here. And because that's the smallest, we don't need that. And that means in this case, our limiting reagent is our CO2. And by default, the excess reagent will be the other guy. Any questions on how we determine that there? Okay, now that we have that, we're looking for our product there. And we can see from our table here that the moles of our product equals X in this case. So the moles of this guy is equal to X, which means we have 2.272 moles of it. And we do want grams in this case, since our actual yield was given to us in grams. So we do need the molar mass of it. And that is 2 times 1401 for the nitrogens, plus 4 times the 1.008 for the hydrogens, plus 12.01 for the carbon, and 16 from the periodic table there for the oxygen. Adding all that together, 60-ish, I think. Like 6006. As our molar mass of our product. So we'll use that as our conversion factor here. And here we do want the grams up on top. So 6006 grams per mole of our product. Again, the moles are going to cancel, going to get us about 136.5 grams of our product here would be produced based off of the equation. And this, what we just calculated, is the theoretical yield. Any questions on that there? We are given the actual yield right here in the problem. So that is our actual yield, which is 120 grams. So now we have the actual yield and we calculated the theoretical yield. So what's left is we could calculate our percent yield by taking the actual divided by the theoretical times 100%. That's going to be 120 grams divided by 136.5 grams times 100%. As we talked about, I think last time as well, when you calculate the percent yield, it doesn't really matter the units as long as they're the same. So you could do grams over grams, moles over moles, whatever it may be. So in this case, we wanted grams because our actual yield was in grams. So 120 divided by 136.5 times 100 and maybe like a 87.91% yield in this particular case. Any questions on that there? Now, again, if you chose to do this method and the question was a little different or want to know a couple of other things, once again, we could easily figure out how much water we also produced here by going back to the table. And if we want to know the moles of water, it also equals X in this case, which would be 2.272 moles of water was produced, which would be the theoretical yield of water in moles. And we can use the molar mass of water, which is 1802 grams per mole. And in a pretty quick fashion, we could also figure out that we would have produced there about 40.94 grams of water, which would be the theoretical yield of water. And obviously, since this is our excess reagent, if we want to know how much of that guy was left over, we could put our X value back into there, and that would give us how many moles of that's left over, which we also can convert to grams if we wanted to as well. Any questions on limiting reagent type problems, percent yield, how to calculate any of that? Yeah. And then we're going to change gears just a little bit, I think, not too much. Here again, I will scroll through the alternative sort of approach where this is again the starting moles of each of those guys. Here's the little calculation that you could do between the two reactants to see if you have enough, in this case, ammonia, to use up all of your CO2. We would then do a comparison between those two numbers and see that we do have enough ammonia, which tells us, just like we saw in our method there, that ammonia is the excess reagent and CO2 here would then be the limiting reagent. Once that's determined, we would then use our CO2 as the limiting reagent and finish the calculation like we did. As you can see, you get the same answer. Again, whichever way you like it. And then obviously our percent yield here. All right, so we're going to talk about solutions a little bit here. Solutions is a homogeneous mixture of two or more substances. It is a mixture, and homogeneous means that it looks the same throughout. Solutions are, again, the guys that receive the aqueous symbols next to it. So they are the guys that get that. A solution, again, is made up of two parts. It is the solute and the solvent. The solute is the smaller part of the solution. The solvent is the larger part of the solution. And typically you dissolve something in the solvent to make a solution, like again, sodium chloride. Take some solid of that with some water. They will come together and dissolve and make a sodium chloride solution. Once again, the name of the solution is the solute. So that's how you know sodium chloride. And if it is ionic, probably a fairly good shot that the solvent would be water. But again, water is not always a solvent, but it's a very common solvent for things that are ionic for sure. And also polar things it works really well with. We usually think of solutions being in sort of the aqueous state. It can also be a liquid state. Again, like our soft drinks, water is the solvent, sugar, CO2, and other things are the solutes. Air is actually a mixture, and can be considered a solution. It's got nitrogen, the major component, with oxygen and other things, depending on what air you're breathing at that moment. Solder, for example, is a solid version of it. But most of the time when we think about solutions, we do think about it in more of the aqueous sort of terms. And I think we've talked about it previously, but there is a difference between aqueous and liquid. Again, liquid is something that's a pure substance by itself, like water, nothing else in there with it. Aqueous is, again, a mixture, which means you got two things together, the solute and the solvent together. Like I said, aqueous solution. So that brings us to solution stoichiometry, and one of the most common units of concentration that we use is molarity. And molarity really is the moles of solute over liters of solution. As I put in lab the other day, molarity basically is moles per liter. And since we really do solve for any of these three things, you can really think of it almost like a formula. And you need to be able to rearrange it because we do use it a lot. So once again, liters would be moles divided by molarity, and moles would be liters times molarity. And that's an important aspect. You do need to make sure that your volume is in liters when you multiply it by the molarity. If you leave it in milliliters, you do not get moles out of that. You get actually millimoles, yeah, which could be okay, but most of the time people think you get moles, and then you're off by a factor of 1,000. So always good practice to convert your volume to liters, and it should be multiplied by the molarity will get you your moles. When you do have a solution, again, like something that is 4.5 molar sodium chloride, it is very important to probably get rid of that big M, as we might have talked about there. So 4.5 moles per liter of sodium chloride. That way you can see both units. It's super common when people leave the big M in calculations. They clearly have no idea where the liters part is. They forget about the volume part of it and not really sure if they should multiply, divide, or those type of things. So it's a really good idea to get rid of the big M when you're doing calculations, and honestly do it more like a dimensional analysis sort of calculation, so you can see the units cancel. You'll usually get the right sort of idea there. By the way, when we talk about molarity and concentration, how molarity works with, for example, an ionic compound like sodium chloride. So if you have sodium chloride, which is a strong electrolyte, as we've talked about, when it is in solution, it is a sodium ion and a chloride ion. And if we had a molarity of this guy of 4.5 molar, sometimes we are interested in just the molarity, for example, of just the ions that are present. So the way that molarity and concentration works here, in terms of if you're looking at an ionic compound and you're interested in what the molarity of the individual ions are floating around that solution is, it kind of works like stoichiometry. So what that means is, for every one of these sodium chloride units, I get one sodium ion, which means that the concentration of the sodium ions that are floating around that solution would be 1 times 4.5 molar, which would give us 4.5 molar of sodium ions. I could also do that between the whole thing and my chloride, and I see for every one of the whole thing, I do get one of the chloride ions, which means, again, I take 1 times 4.5 molar, gives me 4.5 molar of the chloride ions floating around that solution. Now, if I had, for example, calcium chloride, that had a concentration of, say, 2.5 molar. When this guy breaks apart in a solution, what's going to really be floating around are some calcium ions and a couple of chloride ions basically floating around. So when we look at the concentration of the individual ions, in this case, for every one of these guys, we actually get one of these. So for the calcium ions floating around, it would be 1 times 2.5 molar, which would give us 2.5 molar of our calcium ions. But when we look at the whole thing to our chloride, it actually is a 1 to 2 relationship. We get basically 2 for 1 deal here on the chloride. So how that affects concentration or molarity is we actually would multiply the molarity by 2. And for the chloride ion, we would have a 5 molar concentration for those guys that are floating around in there. There's basically twice as much, which means there's twice the concentration of chloride ions floating around in that solution as there is calcium ions. It is clearly not additive, like you had 5 and 2.5 there. You don't get 2.5, but it is sort of proportional of how it breaks apart. That is basically the short version of that calculation. The long version of that calculation is really a stoichiometry calculation, where we would take 2.5 moles per liter of calcium chloride. And for calcium, it is a 1 to 1 relationship. 1 mole of the whole thing gets us 1 mole of the calcium ions. Moles of the whole thing cancel, gives us 2.5 moles per liter of just the calcium ions. And if we did that for our chloride ions, we would have 2.50 moles per liter of calcium chloride. For every 1 mole of calcium chloride, we get 2 moles of the chloride ions. And that gets us our 5 moles per liter of chloride ions. That is the multiplying by 2 part that we did here. That is the multiplying by 1 part that we did there. So that's just a quicker version of doing it without sort of the big calculation. Question on how molarity relates to ions here. A couple of very common conversions when you do need to calculate the molarity of a substance. Grams to moles. So again, molar mass being used to go from grams to moles, and very common milliliters to liters conversion. So 1,000 milliliters to a liter is oftentimes used a lot in these type of calculations. Any questions on that there? Why don't we try this one here? What is the mass of potassium iodide that's required to make 500 milliliters of a 2.8 molar potassium iodide solution? Oh, what is that potassium? Potassium is like 3910 maybe. Iodine is not 3910. Iodine is like 100 and something like that. I can't see that far. Whatever. I can maybe see. Everybody have iodine is 1.9? 1? So 126.19? Sounds good. Thank you. I feel good. I can still see the periodic table. That's a bonus there. I can still see the letters. That's not too bad. All right, so we're looking for the mass in grams. Okay, so let's take a look at it. So in this case, we do have the volume. It's given to us in milliliters, but we can get to liters, so we do have that. We also have the molarity that's given to us. So if you weren't sure, that's the only thing we don't have, which is moles, which would be a good thing to figure out. Since we're looking for grams, then we could use the molar mass to go from moles back to grams. Again, we do need to do a little bit of work here. So first off, we do want to convert our milliliters into liters. So I got to divide by 1,000 there. Milliliters in a liter, going to give us 0.5 liters. Remember that, sometimes it's best to turn this into kind of like a conversion factor here, moles per liter. Number stays with the moles is always per 1 liter when you kind of use it like that. And if you needed to, you could flip it around and use it the opposite way in more of a dimensional analysis approach. So if I do more of a dimensional analysis approach here, we'll take the 0.5 liters. We're going to actually use our conversion factor here so that the liters cancel. Liters 2.8 moles of Ki. Liters here will cancel. If you got an answer at this point, you got something like 1.4 moles of Ki. At this point, we do need to get to grams, so we need the molar mass. So it looks like we're just going to add those two together there, and that's going to give us 166 grams per mole. And we'll use that as our conversion factor here. We do want the grams up on top so that they are left over, and we want the moles to cancel, which will go on the bottom. Remember, a reminder that when you do calculate the molar mass of something, it is solely just based on the formula, regardless if it's in an equation and has a coefficient. You always calculate the molar mass based off of just the formula by itself. So we'll take that times 166. Looks like we will yield something like 232 grams of Ki in this case. Yeah. Any questions on that one there? So what that number means is I would measure out 232 grams of Ki. I would dissolve it in enough water to have a total volume of 500 milliliters. I give it a mixy, shaky, let everything dissolve. and I should be sitting there with a solution that has a molarity of 2.8 molar at that point. Any questions on that one there? All right, so let's try one more here. Let's see, what do I want to try? Let's do what is the molarity of a solution made by dissolving 72.5 grams of calcium chloride in enough water to make 625 milliliters of solution. So give that. Okay, let's take a look. So we're looking for the molarity here. So we need moles and liters. In this case, we are given grams, which we can get to moles. So we essentially have that. We also have the volume here in milliliters, but we can't get to liters. So really just need to do a couple of conversions here. And very commonly, we do need to go from grams to moles. So we'll do our molar mass from the periodic table. That's going to be our 40.08 grams per mole plus 2 times our 35.45. Going to get us 111, we'll call it, grams per mole. So starting with our 72.5 grams of calcium chloride, we're going to convert that into moles. We're going to divide by the grams so that they cancel. So that'll get us 72.5 divided by 111 is 0.6531. At this point, we now have it in moles, and we also need to convert our volume here into liters. And that'll give us 0.625 liters. So now we got both. So molarity here will be 0.6531 moles divided by 0.625 liters. It's like a 104 here, 1.04 units here would be moles per liter. You could leave it like that. Calcium chloride, perhaps. You could also write 1.04 big M calcium chloride as well. So whichever way you want to leave the answer there. Again, as you can see here, I did get rid of, well, I didn't use it here, but you are using it in the calculation. I would get rid of that big M like we did there on the previous example. Question on how to calculate molarity here. All right, so here's a one way you can make a solution of a known quantity. This is a volumetric flask, which we'll use a little bit later on today. Volumetric flask means expensive, also has one marking right about there, and that is the marking for the volume of it. So typically, if you're going to take a solid to dissolve, a lot of times people actually dissolve it a little bit in a beaker with some water first, kind of pre-dissolve it. Makes it easier to go through the funnel. So you don't have to call your teacher over to get it through the funnel later today. Yes, pre-dissolve it first. Then you're going to really want to kind of fill it to about halfway-ish there, not into the neck. That'll give you enough room to kind of continue to mix it and dissolve it. Once it's really dissolved, then you want to take it into the neck and maybe a wash bottle drop or something like that to get your meniscus there to the line. If I go over the line, can I just pour out the solution at that point? I cannot because my solute has dissolved. So once you pour out the solution, you're pouring out your solute, you no longer have the correct molarity there in that particular guy. Don't go over the line, which is the other thing. Yes, like, is that a problem? I filled it all the way to the top, way past the line. Say go find the waste container, into the waste container and try again. Yes. So let's be environmentally friendly and not kill too much chemicals tonight. All right. So another very common process is dilution. And dilution is a procedure where we really add more solvent to a solution to lower its concentration. So a lot of times that solvent is water. So in a lot of cases, we do add just sort of more water to it, but it doesn't always have to be water, but you typically would add more of the solvent to it. The moles of the solute before and after the dilution remains the same. And that is because when you actually look at the definition of what molarity is, that is the moles of solute divided by liters of solution. And once again, the solution is the solute and the solvent, which means when you add more solvent to this situation, you're adding more here, which means you're really increasing the bottom part of our molarity formula, which means if you make the denominator larger, the molarity gets smaller, right? Because you're dividing by a larger number. So that's why the concentration goes down as you do the dilution, because you're adding more solvent, and that basically is adding more solution, and that's the bottom part there of the fraction, and that will make the fraction become smaller, or the number becomes smaller as it gets larger on the bottom. So there is a dilution equation, and most people use M1 V1 equals M2 V2. M1 and M2 are the molarities, and this is usually before the dilution. This is usually after. So usually the twos are kind of your more diluted solution, and your ones are your more concentrated solution. It's like when you get the big gulp right before class with all the ice and it tastes really good, but you leave it in your car and come backwards after class, all the ice is melted. It's a hot day. It doesn't taste as good. You try it though, right? Going, how bad could it be? Then maybe you regret it after you take the dip and stuff like that. It's obviously a lot more diluted as all that water from the ice is now diluted down to your syrup and all that good stuff in your soda. So most of the time, this is the equation that we use. V1 is typically the volume of the more concentrated solution you need. V2 is typically the final volume of the more dilute solution. People also in books nowadays will oftentimes use more of a generic formula for this, which is C1 V1 is equal to C2 V2. And this formula is really the same, but C here is just generic for concentration. And although molarity really is probably the most common one we'll come across, you really could use any type of concentration unit in that formula. Use something like percent mass to mass, percent volume to volume, percent mass to volume. But most of the time we'll use molarity, which is why most people go M1 V1 equals M2 V2, but C1 V1 equals C2 V2, pretty much the same deal. As long as they're the same unit on both sides, that's important. Volume as well, as long as they're both same units on both sides, it's okay, especially if you're using the M1 V1 equals M2 V2. This is probably the only place where it is wise, if you want to. You can leave the volume in milliliters and it'll work out okay. And that's because if you're solving for, say, M2, it would be M1 V1 over V2. And if you did that, you would have molarity times milliliters divided by milliliters. They would cancel and leave you molarity that's left over. Once again, to clarify, if you take milliliters times molarity, you're really taking milliliters times millimoles over milliliters. And the milliliters cancel and you get what are known as millimoles, not moles. They're like moles, but milli of it. Yeah, so about 1,000 factor less. If you take liters times molarity, which is moles per liter, you end up with moles. But millimoles works out okay as long as you divide by milliliters. So if you take you take millimoles and divide it by milliliters, the millis cancel and you're left with moles per liter, which is molarity. So I personally would recommend liters in most situations, 100% of the time, liters when it's just molarity by itself, not doing any type of dilution. Make it to liters for sure. If you happen to be using this dilution equation, you can leave it in milliliters, or you can convert it to liters as well. So it's either way that you want to do it. Any questions on that there? Okay. So let's try that one. How would you prepare 60 milliliters of a 0.2 molar nitric acid solution from a stock solution? Okay, so let's take a look. We are doing a dilution here, no reaction. It's basically nitric acid and nitric acid. So we basically got a bottle there that is 4 molar, and that's more concentrated. We want to make a new solution that has a total volume of 60 milliliters and a molarity of 0.2 molar. So we could use our M1 V1 equals M2 V2 here. Our M1 would be the more concentrated, which would be the 4 molar. Our V1 we do not have. That's actually what we're looking for. Our M2 in this case is the 0.2 molar, and our V2 is 60 milliliters. So putting it in here, M1 V1 equals M2 V2. Solving for V1 would be M2 V2 divided by M1 as we bring this to the other side and divide. And putting in our numbers here, 0.2 molar. Once again, it is okay to leave it in milliliters in this case because the molarities will cancel and I will be left with milliliters in this case as my answer. And if I do that, I'm going to get 0.2 times 60 divided by 4. Looks like I get 3, it looks like there. It's going to give me 3 milliliters of nitric acid. Yeah. First off, question on that calculation. Obviously, if you converted to liters, I think you would be shooting at something like 0.003 liters would be what you would get. What that number represents, and typically when you solve for V1, is that is how much of the more concentrated solution you would take and put in here into your new container. Would I then put 60 milliliters of water into that? I would not, because if I did, my total volume would be 63 milliliters, which is not what I'm shooting for. I am shooting for 60. So a very common question in dilution problems is like how much water you're going to add. And typically how much water you would add is V2 minus V1. So we want to make 60 milliliters. We basically put in there already 3. That means if my math is not too bad there, it's like 57-ish milliliters of water needs to go in with it. We would top this off with 57 milliliters of water. That's going to give us a grand total of 60 milliliters. Give it a mix. And now we should have a solution that has a concentration of 0.2 molar. Question on that. So sometimes people screw that part up and they just see the final volume and go, that's how much water I should add in there. But you already obviously put some volume in by solving for that V1 in this case. Any questions on that there? Let's take a look at one more here. Let's say we had a 55 milliliter 2.5 molar calcium chloride solution. What would be the molarity of the solution or the concentration after we add 105 milliliters of water to it? See what you come up with. I'll do it as well since I've made up all those numbers. best. We have a solution that is 55 milliliters and a concentration of 2.5 molar. We want to know what the solution would be once we actually add 105 milliliters of water to it. That means our M1 in this case is 250. Our V1 there is 55 milliliters. Our M2 is what we're looking for. What's the new concentration? And our V2 in this case is 105 or 160, right? Because we added to the 55 milliliters 105 milliliters. So that's 160 milliliters will be our new total volume, as we had 55 milliliters in there to start with. We just topped it off with 105 milliliters, which will give us our total of 160 in this case. That means when we solve for M2, we want to make sure we use the right one. I'll come up here. So M2 in this case would be M1, V1, V2. Putting in our numbers there from the bottom. We got our M1, which was 2.5 molar. Once again, here we can leave the volume in milliliters. You can convert it to liters if you want. If you do, you should convert them both to liters, obviously, so that the units cancel correctly. Milliliters will cancel in this case. And that's going to give us 2.5 times 55 divided by 160. And we will end up with a molarity of this guy of 0.859 molar, which is obviously less concentrated than what we started with because we added more water to it in this case. Question on dilutions here. Yeah. So dilutions are not too hard, but they can be hard if you do not read the questions correctly. So very common people do not read the questions correctly and answer what they're asking, like how much water, or in a case like this, you added water to it, so they just see the second number and just plug and chug into the equation without reading the actual question. So make sure you do. Any question on molarity, dilutions? Then let's talk about what we're going to do here in just a bit, which is not this, so we'll come back to this. Let's talk a little bit about titrations, which is obviously the big experiment we're kicking off here tonight. Hopefully you brought your sleeping bag. So titrations is a process that is used usually when we have one solution of sort of known concentration, so sort of a known solution, and we use that known solution to help us understand things about a unknown solution. So maybe we don't know the molarity of the unknown solution. Maybe we want to figure out how much volume that we need of the unknown solution to get this reaction to happen. Maybe we want to know the molar mass of the unknown solution. So it's usually a situation where we kind of know something about one. So we have kind of like a known solution, and we have some type of unknown solution. And the process of doing titration, especially acid-base titrations like we're going to do, is we will use a burette, which is a long glass tube, has a on and off switch there, known as the stopcock there. And we have a container. And again, in an acid-base titration, you may have a base up in the burette, or you may have an acid. And down on the bottom there, you'll either have an acid or a base there in the receiving sort of process. So we usually add one sort of drop by drop, if you will, slowly mixing until the reaction is complete. And typically the point where an acid-base titration is complete is what's known as the equivalence point. And the equivalence point in an acid-base titration is the point where the moles of the acid exactly equals the moles of the base. So pretty much you neutralized everybody that was there, the acid and the base. You've added exactly the equal amounts of, if you're adding base to acid, the same moles of each of those. That's not to be confused with the end point of a titration, which is typically where you end your titration. And if you do a good titration, your endpoint and your equivalence point should pretty much be the same spot. Yeah, bad titration, maybe it won't be. But we typically do need some type of indication or indicator really to tell us to stop the titration or to know when the titration is sort of over or the reaction's over. And we do use indicators to help us do that. Indicators like our friend phenolphthalein. That'll be the bonus spelling question there on the next exam. Phenolphthalein is an acid-base indicator, and most indicators actually work over a pH range. So most indicators work over an actual pH range. And by the way, pH of 0 to 7 or below 7 is acidic. Above 7 to 14 is basic, and 7 there is neutral. So for example, phenolphthalein, like we're going to use today, works around like 8.3 to 10-ish. Yeah. And we see a change in color around the equivalence point, hopefully. Phenolphthalein is in acidic solutions, colorless. Yes. In neutral solutions is colorless as well. And in basic solutions, it is pink. Yeah, so it is a pink color there. And that is a pH of 8.3 to 10. Around 8.3, it is actually colorless. Then very quick after, it will turn light pink, super dark pink, dark fuchsia on the back end there of the pH scale. So when we do a titration like this, and when we choose an indicator, we do want to choose an indicator that will actually change color that we could visually see around where your end equivalence point of your titration is. In this case, phenolphthalein works well for the titrations we're doing. We do see that. When we typically do a titration like this, we're really looking for the lightest color of pink that you could get. The lightest, like you got to hold it up to like the whiteboard or white piece of paper to kind of see the tinge of pink. Super dark pink is usually not the color we're going for, but a lot of times what people end up with. And it can happen, believe it or not, with just one drop. Like you got no color and you had one drop and you're like, wow, that's really pink at that point. Yeah, so it can actually really happen very quickly. And the reason it can really happen really quickly is just to explain that to you so you're not upset later. And we'll hear the common thing that everybody says, I just added one drop and it went like super dark pink on me. If you actually look at a titration curve as it's happening, which you will in 200B, if the equivalence point is right about here, and this is the volume, say, of base you're adding, when we get close to the equivalence point, we sort of jump up pretty vertical. And when we jump up pretty vertical on this scale, on the y is the pH, which means between here and here, as we approach the equivalence point, that is a big change of pH, right? It goes from like real low pH to very high pH. And that means when we look at our indicator, it goes from low pH to high pH, right? Within a lot of volume or not a big volume change between all those spots. The volume does not change very much at all in that area there. So you could be super careful. You could be adding it drop by drop, and you could add one drop, and that is enough to change the pH of that solution by a lot. And that will make your indicator go from like no color to super dark pink within one drop, which is a common thing people say. I just added that one drop and it's all this big change. And the reality of it is, most of the time in titrations like we're doing here, we're interested in the volume at the equivalence point, which means if I were to stop right there at the equivalence point, or even if I missed it by a drop there, even it was maybe just shy of it there, is there a big difference between those three green dots in terms of the volume? No, because we go straight down, it's pretty much the same volume, which means if you're really careful as you're doing your titrations and you're not titrating like me, which is a bad example where you just open it up, walk away, come back, turn it off and go, cool, I'm pink, I'm done, you know. But if you're really careful as you're going through it and you miss it by a drop or two, in the grand scheme of things and the calculations we're going to do, not going to make a big difference. And I won't make you redo it. Other teachers will go, too pink, go redo it again. It's not light enough. But if you're really not careful, and why some teachers will tell you to go redo it again is if you're not careful and you did titrate like me and walked away, which you should never do, and you come back, you could get the same color pink way over here. Yes, which means how close am I to my equivalence point volume? I'm pretty far away from it at that point, which means if you're really not careful and you really overshoot it, not by a drop or two, you're going to be very far away from your equivalence point, and it will make a difference. So a lot of times when you do titrations, it's actually more important not to get so hung up on the color part of it, but to actually have volumes that are very consistent every time you get to the equivalence point. So you usually do multiple trials, and if those volumes to reach the equivalence point is about the same, you're probably going to be in good shape in that case. Also, the magic word of extra and credit usually helps a lot with like light pink coming out after nobody could hit it. So you say those two words and it's like, well, everybody could do light pink at this point. So maybe we'll see how that works later. So that's what happens sometimes. So don't get discouraged if you just add one drop and go super pink. It's really more important that the volumes are pretty close to each other. You should try to get the lightest color that you can get. There's ways that you could do that. For example, here you can see on the burette, you could actually, as you're titrating, let a drop kind of form. You could take your wash bottle with some deionized water and kind of wash it in. And that's what's sometimes referred to as adding a half a drop, kind of diluting it as it goes in. And that sometimes will help with not getting that big change in color as you approach the equivalence point. You usually know you're approaching the equivalence point with your indicator, because every time you drop your drop some sodium hydroxide, for example, the solution will turn pink and then it'll go away. It'll turn pink, it'll go away. As you mix, it'll turn pink, it'll go away. It'll turn pink, stay longer, then go away. Turn pink, stay a little bit longer, go away. You'll start to see it stay longer and longer. You know you're approaching the equivalence point. At that point, you might want to slow down and kind of do maybe like a half a drop until you get to that really nice light color of pink that's in there. Any questions on that there? Now, when we have titration problems, they're really solution stoichiometry problems. And the good news about solution stoichiometry problems is it really is the same thing as a stoichiometry problem, except that how we get moles usually, and we oftentimes will use molarity. So we do follow the same sort of 4 steps here. We want to make sure we have a balanced equation. We want to convert to moles. We could have a limiting reagent problem, so we want to watch out for that as well. We will then do our mole to mole relationship, and we will convert moles to some other unit. In this case, if it's not, again, a limiting reagent problem, I probably would not be using a nice table. I'd just be following the basic stoichiometry steps in these calculations as we talked about. Now, the difference comes as we get to here when we convert to moles. We oftentimes will use our molarity in this case, and to convert to moles, our moles would be liters times molarity. So instead of using grams and molar mass to get to moles, we use the volume and the molarity to get to moles. Also on the back end of the calculation, we oftentimes will use molarity on the back end of the calculation as well, either solving for volume or actually solving for molarity on the back end of the calculation. Everything in the middle is pretty much the same, except for kind of using those different things. So if we look at this problem here to finish up on what volume of sodium hydroxide is required to titrate sulfuric acid. So we want to start with an equation. So we have sulfuric acid here going to react with sodium hydroxide. This is going to be a double displacement reaction. The H is going to switch partners, and when sodium and the sulfate is going to come together, this is going to get us water, which is always produced in an acid-base reaction, and we will get some sodium sulfate, which we want to make sure we start with the right formula, which would be Na2SO4. Like anything else, we want to make sure that it is balanced, and in this case, it is not balanced, so we do need to put a 2. And I think we need a 2 there. And now we are balanced at that point. So we want to make sure that we have a balanced equation. Any questions on that equation there? Now, if we look at our problem here and see what was given to us In this case, we're looking for the volume here of sodium hydroxide, and we do have the molarity. For our sulfuric acid, we have the volume and we have the molarity. So I first know that this is not a limiting reagent problem because I can only get to moles of sulfuric acid, and I can get to moles of sulfuric acid because I have both the volume and the molarity given to me, so I could get to the moles of it. I can't get to the moles of sodium hydroxide, so I know it's not a limiting reagent problem. It is just a basic stoichiometry problem at this point. So we would roll into our second step, which is to take basically what we can and convert into moles, which is this guy. So we would want to convert our volume into liters. So divide it by 1,000, which will give you 0.025 liters. We're going to times it by the molarity of the sulfuric acid, which is 4.5 moles per liter. The liters will cancel, and this will give me 0.025 times 4.5, 0.1125 moles of sulfuric acid. So this is equivalent to our second step in stoichiometry, converting to moles. Again, instead of using grams of molar mass, molarity and volume here to do that. Any questions on that? We're not ultimately interested in sulfuric acid. We're interested in sodium hydroxide, and that is the stoichiometry part of the program here. We're going to go to the equation and find those two things, and we can see from the equation for every 1 mole of sulfuric acid, we get 2 moles of sodium hydroxide. So the next part is really just like a basic stoichiometry problem. We're going to go from our moles of sulfuric acid using the stoichiometry from the equation, 2 moles of sodium hydroxide up on top, 1 mole of sulfuric acid on the bottom. The moles of sulfuric acid will cancel. Times it by 2, basically. Going to give us 0.225 moles of sodium hydroxide. So that's like our third step. Use the mole to mole relationship here. First off, any questions on that there? Really, the last step is also very similar, except at this point, we are looking for the volume of sodium hydroxide. We're not looking for the grams. So normally at this point, we would go to the periodic table, get the molar mass and figure out the grams, but we are looking for the volume. What we know about sodium hydroxide is the molarity of it. So we know for the sodium hydroxide that it is 1.42 moles per liter. So we could use that as a conversion factor along with the moles we just calculated to figure out the volume. And just doing a dimensional analysis way, we want the moles to cancel, which means we want to put the moles on the bottom, the liters up on top. That means that the moles of sodium hydroxide from the molarity will cancel those guys out. And I'll go up on top here. That's going to give us 0.158 liters is the volume that we have here. And if we want milliliters, we should multiply it by 1,000, right? Milliliters is a liter. Gives us about 158 milliliters of sodium hydroxide. So in this case, we would need about 158 milliliters of that sodium hydroxide to completely neutralize and use up all of that sulfuric acid that is present. Questions on that calculation? As you could hopefully see, it really is just the stoichiometry calculation, basic stoichiometry calculation. The difference is how you get the moles, how you get the liters. At the end, for example, here, if we got the moles of sodium hydroxide and didn't know the molarity, but knew how much volume of sodium hydroxide we use, like if we use 25 milliliters of the sodium hydroxide, we could convert that into liters and we could actually calculate the molarity at the end of sodium hydroxide. So those are 2 common endings to titration problems and solution stoichiometry problems. How much volume, and if we had the other information, we could have went to molarity if we were given the volume instead of the molarity of the sodium hydroxide. Any questions on that there? All right.